August 12, 1940, Erprobungsstelle Rechlin, Mecklenburg, Germany. The morning sun cast long shadows across the hexagonal perimeter road as Major Werner Mulders circled the unfamiliar aircraft on the concrete apron. 3 days earlier, this supermarine Spitfire Mark I had been coded GX by No. 222 Squadron RAF. Now it bore the crude markings 5+2 hastily painted over British roundels. The fighter had force-landed at Le Touquet airfield on June 1st after its pilot misjudged his fuel reserves during operations over Dunkirk. German recovery teams had towed it intact from the beach. Mulders ran his hand along the elliptical wing's leading edge. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The aluminum skin felt impossibly thin compared to the Messerschmitt Bf 109 he had flown to 40 aerial victories. Everything about this machine seemed delicate, almost fragile. Yet RAF pilots had used these fighters to inflict losses that troubled Reichsmarschall Hermann Göring's assurances of Luftwaffe superiority. The test assignment was straightforward. Evaluate the Spitfire's handling characteristics, performance envelope, and combat effectiveness against the 109. Document its strengths and weaknesses. Provide tactical recommendations for engaging this opponent over England in the coming weeks. What Mulders could not yet know was that this examination would reveal a truth more troubling than any tactical assessment. The engine beating inside this enemy fighter represented a philosophy of power generation that German engineering had not achieved. The British fighter rested beside a captured Hawker Hurricane in the experimental evaluation area. Both aircraft awaited systematic analysis by Germany's premier test facility. Rechlin had been the Luftwaffe's official testing ground since 1934, located approximately 100 kilometers northwest of Berlin. 3 interconnected airfields provided space for evaluating captured enemy equipment, alongside developmental German types. The turf-surfaced main field was surrounded by the characteristic hexagonal perimeter road. Smaller auxiliary fields at Rogentin and Lars handled overflow operations. The facility's mission extended beyond simple flight testing. Engineers here determined usability, maximum performance, operational limitations, and maintenance requirements for every aircraft type the Luftwaffe considered deploying. Captured enemy machines received the same thorough examination, seeking tactical insights and technical revelations. The Spitfire would surrender both. Mulders had been selected for this evaluation based on combat experience and technical understanding. Born March 18, 1913 in Gelsenkirchen, he had joined the Luftwaffe in 1934. Service with the Condor Legion in Spain provided early combat against Republican forces, where he developed tactical innovations in fighter employment. Returning to Germany, he had commanded Jagdgeschwader 51 through the Battle of France and the opening phases of operations against Britain. His 40 victories made him Germany's leading ace. His engineering knowledge made him uniquely qualified to assess enemy technology. The examination began with exterior inspection. Mulders walked the aircraft's perimeter, documenting construction methods and structural details. The Spitfire's design reflected priorities fundamentally different from German fighters. Where the 109 emphasized ruggedness and ease of mass production, this British machine pursued aerodynamic refinement above all else. The wing's graceful elliptical platform minimized induced drag, while maximizing internal volume for fuel and ammunition. Smooth, stressed skin construction eliminated unnecessary protrusions. Even the cockpit canopy blended seamlessly into the fuselage contours. Childishly easy to enter, Mulders would later write in his evaluation report. The cockpit access required simply swinging open the side-hinged canopy and stepping onto the port wing route. No awkward scrambling over wing edges, as in the 109. The British had designed this fighter for pilots who might need to enter and exit quickly, perhaps multiple times per day during intensive operations. German fighters assumed pilots would remain with their machines for extended periods. The instrument panel appeared remarkably uncluttered compared to German practice. Essential flight instruments clustered directly ahead of the pilot. Engine controls fell naturally to hand on the left side panel. No complex propeller pitch controls demanding constant attention. Simply a two-position selector, fine pitch for takeoff and climb, coarse pitch for cruise. The British had deliberately simplified pilot workload, trading control flexibility for operational ease. Mulders settled into the seat, adjusting the Sutton harness. The cockpit felt small, almost intimate. A pilot fitted into this space rather than occupying it. Everything was positioned within easy reach. Throttle quadrant on the left, mixture control, supercharger selector, and radiator flap controls alongside. Undercarriage selector on the right, gun sight mounted centrally. The design reflected careful attention to pilot ergonomics, perhaps stemming from racing experience. Supermarine had built the S-6 seaplane that won the Schneider Trophy in 1931. That aircraft's pilot sat in a cockpit barely larger than a coffin, where every control had to be instantly accessible. The lessons had transferred to this fighter. He studied the engine controls more carefully. The throttle quadrant showed clear markings for maximum continuous power and emergency boost settings. Plus 6 pounds per square inch for normal operations, plus 12 pounds for combat, but only for 5 minutes maximum before risking engine damage. The British were deliberately trading engine longevity for peak performance, accepting that combat engines might require premature replacement in exchange for temporary power advantages. The ignition and starter procedures proved surprisingly simple. 2 magneto switches, 1 engine primer pump, 1 starter button. German fighters required more complex startup sequences involving multiple fuel cocks, throttle positions, and timing considerations. This Spitfire could be started quickly by pilots under stress, perhaps scrambling to intercept incoming raids. Speed of launch mattered more to the British than engine preservation. Ground personnel from Rechlin's technical evaluation section gathered around the aircraft. Oberingenieur Hans Doppler, chief of propulsion analysis, carried a thick folder of notes and specifications. His team had already dismantled one of the Spitfire's Rolls-Royce Merlin engines, measuring components and documenting construction methods. What they found had generated considerable discussion at Rechlin's technical meetings. Today's flight test would provide operational context for those discoveries. The engine is a Merlin 3, Doppler explained, opening the cowling access panels. Liquid-cooled, 12 cylinders in 60° V configuration, 27 litres displacement, maximum power approximately 1,030 horsepower at takeoff, using 100-octane fuel. The RAF only recently converted to the higher octane fuel. Previously, they used 87 octane, same as we do. The switch provides approximately 200 additional horsepower. Mulders leaned in to examine the exposed power plant. The engine appeared almost crude compared to Daimler-Benz precision engineering. Castings showed rougher finishes. Components fit together with what seemed like excessive tolerances. Yet the British claimed reliable operation from these engines across thousands of flight hours. Either their quality standards were lower, or they had achieved reliability through design philosophy rather than manufacturing precision. Note the supercharger installation, Doppler continued, pointing to the starboard side of the engine. Single-stage, single-speed, centrifugal compressor. Very simple. The DB601 has hydraulically controlled variable-speed supercharger drive, allowing optimal boost across the altitude range. This British unit runs at fixed speed, with critical altitude around 18,000 feet. Above that, power falls off rapidly. Their design optimizes low-altitude performance, probably for defensive intercept operations. Our DB601 maintains power to higher altitudes, better for offensive operations. The propeller drew Mulder's attention. A 2-blade de Havilland metal unit, surprisingly large at 10 feet diameter, but the pitch control showed only 2 positions, fine and coarse, no constant speed mechanism allowing automatic optimization across the flight envelope. This is a significant weakness, Doppler noted. In combat, the pilot must manually select pitch, fine pitch for takeoff, climb, and tight maneuvering, coarse pitch for high-speed flight. But if he selects fine pitch at high speed, the engine overspeeds and risks damage. If he selects coarse pitch at low speed, the engine lugs and loses power. The pilot must constantly attend to propeller management during combat. Our constant speed propellers handle this automatically, freeing the pilot to focus on tactics. Mulders filed this observation for his tactical assessment. In swirling dogfights, British pilots would be distracted managing propeller pitch, while German pilots simply maintained optimum throttle settings. Small advantages accumulated into combat superiority. The engine startup proved uneventful. Mulders activated the battery, checked magneto switches, pulled the primer pump 6 times, set throttle slightly open, and pressed the starter button. The Kaufmann cartridge starter fired with a sharp crack. The propeller rotated through compression, hesitated, then caught as fuel ignited in the cylinders. The Merlin settled into smooth idle with a characteristic burble from the exhaust stacks. British engines sounded different than German power plants. The Merlin's exhaust note carried a rougher edge, less refined but somehow more aggressive. Oil pressure rose smoothly. Coolant temperature climbed toward operating range. All instruments showed normal indications. The engine felt responsive to throttle movements, accelerating cleanly without hesitation. Whatever manufacturing shortcuts the British had taken, they had not compromised basic reliability. Mulders signaled for chocks removal. He advanced the throttle to taxi power, feeling the fighter respond. The tail came up almost immediately, providing excellent forward visibility. The 109 required careful attention during ground handling, its narrow undercarriage demanding constant rudder corrections. This British fighter tracked straight with minimal pilot input. The widely spaced main wheels provided stability. The pilots who flew this machine could focus on pre-takeoff checks rather than fighting directional control. Rolling toward the runway threshold, Mulders completed the pre-takeoff checklist. Trim for takeoff. Mixture rich. Propeller pitch fine. Radiator flap open. Fuel sufficient. Magneto check showed both ignition circuits functioning normally. The British had designed this airplane for rapid turnaround between sorties, operated by pilots who might be exhausted from multiple missions per day. Every system was designed for simplicity. He lined up on the grass runway and smoothly advanced the throttle to full power. The Merlin responded instantly, pulling the fighter forward with strong acceleration. No tendency to swing right from propeller torque, at least nothing requiring significant rudder correction. The tail lifted after barely 50 meters. At 110 kilometers per hour indicated, Mulders eased back on the stick. The Spitfire left the ground cleanly, climbing away at a comfortable angle. Landing gear retracted with simple hydraulic operation, no manual pumping required. The aircraft felt light and responsive. Control forces were lower than the 109 at all speeds, requiring gentle inputs. The fighter seemed eager to maneuver, almost inviting aerobatic flight. British designers had optimized handling qualities above all else, creating a machine that even average pilots could fly effectively. German fighters demanded more skill, but rewarded proficiency with superior performance. Climbing through 3,000 meters, Mulders began the systematic evaluation. First, level speed runs at various altitudes, then climb performance measurements, finally combat maneuvers, rolls, loops, tight turns, high G pullouts, negative G pushes, and recovery from extreme attitudes. Every test repeated multiple times to confirm results. Rechlin's procedures were thorough. The level speed tests revealed the Spitfire's strengths and limitations. At sea level, maximum speed reached approximately 460 km per hour with emergency boost, comparable to the 109E model, perhaps slightly slower. At 3,000 meters, both fighters performed similarly. But above 5,000 meters, the British fighter began losing the advantage. The single-speed supercharger could not maintain manifold pressure as ambient air density decreased. The DB601's more sophisticated supercharger system provided better high-altitude performance. Climb performance impressed Mulders. From sea level to 5,000 meters, the Spitfire climbed faster than the 109. The lower wing loading and cleaner aerodynamics overcame the small power disadvantage. British interceptors could reach altitude quickly to engage incoming bomber formations, trading ultimate performance for initial climb capability. Smart defensive thinking. But the turn performance stunned him. At combat speeds around 400 km per hour, the Spitfire could complete a full 360-degree turn in approximately 18 seconds. The 109 required 22 seconds. In sustained turning combat, British pilots could gradually gain angles on German attackers, eventually maneuvering into firing position. The advantage was not subtle, it was decisive. Mulders pulled into a series of increasingly tight turns, feeling the G-forces build as turn radius decreased. The controls remained light and responsive throughout. No tendency toward departure or spin. Just smooth, predictable maneuvering. A pilot could fly this fighter at the edge of its envelope with confidence. The 109 became more difficult to handle as speed decreased, requiring careful attention to avoid spins. This British machine seemed forgiving of pilot errors. High-speed handling revealed different characteristics. Above 500 km per hour, control forces increased significantly. The ailerons became heavier, requiring more effort to initiate rolls. The British had not installed trim tabs on the ailerons, perhaps considering them unnecessary weight. At combat speeds, the controls felt balanced, but in high-speed combat or when diving to escape, the pilot had to muscle the aircraft through maneuvers. The negative G test provided the most revealing moment. Mulders rolled inverted and pushed forward on the stick, subjecting the aircraft to negative gravity load. The engine immediately began coughing, sputtering, losing power. As the negative G load continued, the Merlin stopped completely, propeller windmilling uselessly. The British carburetor could not handle inverted flight. Fuel starvation killed the engine within seconds. This was the critical weakness. In combat, when a 109 pilot wanted to break contact and escape, he simply pushed the stick forward and dived away. Negative G load pushed fuel into the cylinders, maintaining power throughout the maneuver. But a Spitfire, attempting the same escape, would suffer engine failure, leaving the pilot defenseless during the critical seconds of disengagement. German pilots could exploit this mercilessly. Mulders rolled upright and the Merlin restarted immediately as positive G returned. But those seconds of powerlessness would be fatal in combat. The British knew this limitation. Their tactical doctrine emphasized fighting in the vertical plane, using climbs and loops rather than negative G maneuvers. Their engines forced them to accept this constraint. But why? Why had British engineers accepted such an obvious weakness? The answer lay in the power generation philosophy embodied in the Rolls-Royce Merlin engine beating beneath the Spitfire's cowling. Understanding that philosophy would require looking deeper than flight characteristics. It would require examining the engine itself. After landing and shutting down, Mulders joined Doppler's team in the engine examination facility. The dismantled Merlin lay spread across multiple workbenches, every component labelled and measured. What the engineers had discovered was being systematically documented for eventual presentation to the RLM Technical Directorate in Berlin. The findings would prove more significant than anyone yet realized. "We have analyzed the complete engine," Doppler began, spreading technical drawings across the main workbench. The British approach to power generation differs fundamentally from Daimler-Benz philosophy. Understanding those differences explains both the engine's capabilities and its limitations. The Merlin's construction embodied British engineering priorities. The engine used a conventional upright V configuration rather than Daimler-Benz's inverted design. This simplified cowling but raised the thrust line, affecting aircraft balance. The crankcase was cast aluminum alloy, light but less rigid than German practice. Separate cylinder blocks bolted to the crankcase rather than being integral with it, simplifying manufacturing but creating more potential leak points. "Note the displacement," Doppler continued. 27 litres versus 33.9 litres for the DB601. They achieve similar power output from smaller displacement through higher operating speeds and boost pressures. The Merlin can sustain 2800 RPM continuously. Our engines typically limit continuous operation to 2400 RPM. The British accept higher mechanical stresses in exchange for more power from lighter weight. Moulders examined the piston assembly. The components appeared delicate compared to German equivalents: thinner crown walls, less metal in the skirt, higher compression forgings rather than traditional castings. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Everything was built to minimum weight compatible with survival under stress. British designers were trading longevity for performance, accepting that engines might require overhaul after fewer hours in exchange for superior power-to-weight ratios. The valve train showed similar priorities. Overhead camshafts operating the valves directly through rocker arms, minimal mass in the reciprocating components. The system could sustain higher RPM than German pushrod designs, but required more frequent adjustment and maintenance. British logistics apparently accepted increased maintenance burden in exchange for better performance. The supercharger system deserves particular attention, Doppler said, pointing to the centrifugal compressor housing. Single stage, driven at fixed ratio from the crankshaft, very simple, but it only achieves critical altitude around 18,000 feet. Above that, manifold pressure falls rapidly and power decreases. Our variable speed system maintains boost to higher altitudes through hydraulic coupling that automatically adjusts supercharger speed. More complex, heavier, but more effective across the operational envelope. But the carburetor system revealed the Merlin's most significant limitation. The SU carburetor used a float bowl for fuel metering, same as automobile practice. Simple, reliable, and effective under positive and neutral G loads. But any negative G lifted fuel away from the pickup, causing immediate starvation. The Germans had adopted direct fuel injection specifically to avoid this problem. High-pressure pumps forced fuel directly into cylinders, regardless of aircraft attitude. The DB601 could sustain full power through any maneuver: inverted flight, outside loops, negative G pushes. British fighters could not. Why did they not adopt fuel injection? Moulders asked. Surely they understand the advantage. We believe they tried, Doppler replied. Fuel injection requires precision manufacturing of pump components, operating at extremely tight tolerances under high pressures. We had to develop special alloys and machining techniques to make reliable systems. The British probably attempted similar development, but could not achieve the required precision with their manufacturing capabilities. Or perhaps they simply decided the complexity outweighed the benefits for their tactical employment. Their defensive doctrine may not require negative G maneuvering. This was the first hint of a larger truth. The Merlin's design reflected not just different engineering priorities but different industrial capabilities. British manufacturing produced this engine through methods that emphasized production quantity over individual component precision. The approach worked for their strategic situation, requiring large numbers of reliable engines quickly. But it meant accepting limitations that superior German engineering had overcome. The connecting rods demonstrated this philosophy clearly. German practice used roller bearings between rod and crankpin, requiring precision grinding of bearing races, but providing low friction and long life. British practice used plain bearings, simply bronze bushings pressed into the rod ends. Much simpler to manufacture. Adequate life under operating stresses. But higher friction meant energy waste and increased wear. The British accepted mechanical inefficiency in exchange for manufacturing simplicity. Calculate the specific power output, Moulders suggested. Power per litre of displacement. That reveals how hard they are pushing the design. Doppler consulted his notes. The Merlin 3 produces approximately 1,030 horsepower from 27 litres. That gives 38 horsepower per litre. The DB601 produces approximately 1,175 horsepower from 33.9 litres, giving 34.6 horsepower per litre. The British are extracting more power from each litre of displacement. They achieve this through higher RPM, higher boost pressures, and higher thermal stresses. Their engines run hotter, wear faster, and require more frequent overhaul, but they get more peak power from less weight. This was sophisticated engineering but not superior engineering. The British had optimized one aspect of performance while accepting compromises elsewhere. They needed lightweight, powerful engines that could be manufactured quickly in large quantities. They got exactly that. The Merlin met their requirements perfectly, but it embodied different priorities than German engines, reflecting different strategic circumstances. Mulders reviewed the flight test data one final time before preparing his report. The Spitfire handled beautifully within its design envelope. It turned better than the 109. It climbed faster at low altitude. Its controls were lighter and more harmonious. British pilots flying this machine effectively could challenge German fighters in most combat scenarios, but the engine's limitations created exploitable weaknesses. The carburetor's intolerance of -G meant Spitfire pilots could not execute certain escape maneuvers. The two-position propeller required constant attention during combat, dividing pilot focus. The supercharger's limited altitude performance gave 109 advantages above 5,000 meters. These weaknesses could be systematically exploited through proper tactics. His report to JG-51 headquarters would emphasize these findings. Engage Spitfires in turning combat only when absolutely necessary. Use superior high-altitude performance when possible. Exploit the -G limitation by breaking combat through forward stick inputs. Force the British onto the defensive, where their strengths become less relevant. Apply German advantages systematically to negate British capabilities. The tactical recommendations would prove valuable over England in the coming weeks, but the engine analysis raised questions that tactical employment could not answer. Why had British engineers accepted carburetor limitations when the solution existed? Why had they not developed variable speed superchargers similar to German practice? Why did their manufacturing produce engines that met requirements but lacked the precision refinement of Daimler-Benz products? The answers lay not in British engineering capability, but in British industrial philosophy and strategic circumstance. Understanding that philosophy would require examining not just what the Merlin was, but what it was designed to be. A power plant that could win a desperate defensive war through quantity, reliability, and rapid production rather than through individual excellence. The British were fighting a different war than Germany, and their engines reflected that reality. What Mulders and the Rechlin engineers discovered during those August days in 1940 was that superior engineering could manifest in unexpected forms. The Merlin was not a better engine than the DB601 by most technical measures. It displaced less, weighed slightly more per horsepower, and lacked the sophisticated systems German engines employed. But it achieved its design objectives more successfully than any German engine achieved theirs. The British needed engines that could be manufactured by factories with limited machine tool precision. They needed designs that mechanics with basic training could maintain. They needed power plants that used materials available despite wartime shortages. They needed systems simple enough to remain reliable under the stress of continuous combat operations. The Merlin delivered all of this while providing competitive performance against Germany's best fighters. This was a different kind of engineering excellence. Not the pursuit of perfection in individual components, but the achievement of optimal system integration within real constraints. Not maximum theoretical performance, but maximum practical effectiveness. Not what was possible in ideal circumstances, but what was necessary under wartime conditions. British engineers had designed not for peacetime competitions, but for industrial warfare. The implications would become clearer as the war continued, and British production scaled to levels Germany could not match. The Merlin's simplicity allowed faster production. Its accessibility allowed rapid training of maintenance personnel. Its tolerance of manufacturing variations allowed production to spread across multiple factories with different capabilities. These advantages compounded over time, eventually producing material superiority that German engineering excellence could not overcome. But that realization still lay in the future. In August 1940, Mulders completed his report with tactical recommendations that would help German pilots exploit Spitfire weaknesses. His assessment acknowledged British engineering skill while identifying exploitable limitations. The captured fighter would continue flying at Rechlin, providing training opportunities for pilots preparing to face this opponent over Britain. The aircraft would eventually be transferred to fighter units for tactical familiarization. German pilots would practice interception and engagement techniques against the actual machine they would face in combat. Photographs would appear in propaganda films, showing German fighters successfully engaging the captured Spitfire. The message was clear: German engineering could evaluate, understand, and defeat this British opponent. Yet beneath the confident assessments and tactical recommendations lay a truth that few yet recognized. The British had not built the best fighter engine using available technology. They had built the right fighter engine for their strategic circumstances. They had optimized not for technical excellence measured in laboratory tests, but for operational effectiveness measured in sustained combat operations. They had created a weapon system that could be produced in quantity, maintained under stress, and operated effectively by average pilots fighting a defensive war. Part 2. The collision with reality. The summer of 1940 passed into autumn. German fighter units applied the tactical lessons learned from Rechlin's evaluation. They exploited the Spitfire's negative G weakness. They fought at higher altitudes where supercharger advantages favored German fighters. They forced engagements where propeller pitch management distracted British pilots. The tactics worked. British losses mounted. But the strategic situation shifted in ways tactical excellence could not address. The Battle of Britain concluded without achieving air superiority necessary for invasion. German attention turned eastward toward the Soviet Union. The Luftwaffe redeployed to new theaters where different challenges awaited, and British factories continued producing Spitfires and Merlins in quantities that slowly accumulated into overwhelming material advantage. The numbers told a story that tactical assessments missed. In 1940, Rolls-Royce factories at Derby, Crewe and Glasgow produced approximately 12,000 Merlin engines. The new Ford factory at Trafford Park, Manchester, began production in May 1941. By year's end, British Merlin production reached approximately 23,000 engines annually. German production of DB601 engines totaled approximately 19,000 units across the engine's entire production run from 1937 through 1943. The British were not building better engines, they were building more engines. The Merlin's design philosophy enabled this production advantage. Simplified manufacturing processes allowed rapid factory expansion. Reduced precision requirements permitted employment of semi-skilled workers. Standardized components facilitated production across multiple facilities. The British had designed for quantity, accepting compromises that German engineering would never tolerate. In September 1940, the British government approached American automobile manufacturers about licensed Merlin production. Henry Ford initially agreed but withdrew after pressure from isolationist constituencies. Packard Motor Car Company accepted the contract. The deal represented $130 million, equivalent to approximately $3 billion modern dollars. It was the largest single manufacturing contract in aviation history to that point. Packard engineers visited Derby to study Merlin production methods. What they discovered shocked them. Rolls-Royce drawings used British projection standards and tolerances too wide for American mass production requirements. 20,000 drawings required complete redrafting to Packard's standards. The British had not provided precise tolerances because British manufacturing did not require them. Skilled workers adjusted components during assembly to achieve proper fit. This was acceptable for low-volume production. It was unacceptable for American industrial methods. Packard spent months converting the Merlin for true mass production. They redesigned the engine block as a two-piece assembly rather than single casting. They standardized fasteners and thread specifications. They established dimensional tolerances, measured in thousandths of an inch, far tighter than British practice required. They created manufacturing processes where precision came from tooling rather than craftsmen. The first Packard-built Merlin ran in August 1941. By April 1942, Packard was producing 510 engines per month. By 1944, monthly production reached approximately 2,000 engines. total Packard Merlin production exceeded 55,000 engines by war's end. The Americans had taken a British engine designed for simplified manufacturing and made it even simpler, even more suitable for mass production, even more aligned with industrial warfare requirements. The irony was profound. German engineers had examined the Merlin in 1940 and correctly identified its technical limitations. They understood the carburetor weakness, the propeller issues, the supercharger restrictions. They documented these findings thoroughly. What they failed to understand was that these limitations were acceptable trade-offs for a different kind of superiority: industrial superiority. German engine production reflected different priorities. The DB601 embodied engineering excellence, direct fuel injection, variable speed supercharger, precision machined components, sophisticated systems integration. Each engine represented hundreds of hours of skilled labor. Each required materials in increasingly short supply as the war progressed: nickel for valve faces, cobalt for magnets, precision alloys for bearings and gears, complex machining equipment operating to tight tolerances. When Germany invaded the Soviet Union in June 1941, industrial demands multiplied. The Eastern Front consumed men, machines, and materials at rates no one had anticipated. Luftwaffe losses required constant replacement. Fighter production increased, but engine production could not keep pace. The sophisticated systems that made German engines technically superior also made them difficult to produce in necessary quantities. By 1942, material shortages forced engineering compromises. Nickel content in exhaust valves dropped from 13.5% to 8%. The valves became insufficiently corrosion-resistant, scaling in use. The scale caused pre-ignition, leading to detonation and engine failure. This was the primary reason the DB605, successor to the 601, could not use full manifold pressure. The engine was rated for higher boost, but materials shortages prevented safe operation at design specifications. The DB605 entered production in 1942 as an improved DB601. Displacement increased from 33.9 litres to 35.7. Maximum RPM increased from 2600 to 2800. Power output rose from 1350 to 1475 horsepower. Approximately 42,400 DB605 engines were built, making it the second most produced German aircraft engine after the Junkers Jumo 211. But production numbers told only part of the story. Many DB605 engines reached operational units with known defects. Ball bearings were replaced with plain bearings to conserve materials. This change, combined with increasingly poor synthetic lubricants produced from coal, caused serious reliability problems. Engine fires became common. Emergency power settings were initially forbidden to prevent failures. Daimler-Benz redesigned bearings and added oil coolers. The Reich Air Ministry designated the DB605 a sick engine. Problems were never fully resolved by war's end. German engines reflected the industrial reality of a nation fighting on multiple fronts against opponents with superior material resources. They embodied engineering excellence constrained by material shortages, production limitations, and strategic overextension. British engines reflected the industrial reality of a nation fighting for survival with limited domestic resources, but enormous potential Allied production capacity. They embodied engineering pragmatism optimized for quantity, reliability, and ease of manufacture. The Merlin continued evolving throughout the war. The single-stage supercharger that Mölders had criticized in 1940 gave way to two-stage designs, providing excellent high-altitude performance. The Merlin 60 series, introduced in 1942, featured two-speed, two-stage supercharging. Critical altitude increased from 18,000 feet to 30,000 feet. Power output at altitude nearly doubled. These engines transformed Spitfire performance and enabled the P-51 Mustang to become the war's premier long-range escort fighter. Packard produced the Merlin 60 series as the V-1653. This engine powered Mustangs that escorted American bombers from Britain to Germany and back. The combination of North Americans' excellent airframe and Packard's license-built British engine created a fighter that dominated European skies from 1944 onward. German fighters, powered by increasingly unreliable engines suffering material shortages, could not match the sustained operational tempo Allied fighters maintained. Total Merlin production exceeded 168,000 engines by war's end. Rolls-Royce produced approximately 82,000 at Derby, Crewe, and Glasgow. Ford's Trafford Park facility built 30,000. Packard produced 55,000. Small numbers came from other manufacturers, including Continental Motors. The Merlin powered 19 different aircraft types during the war, plus extensive families of Spitfire and Mosquito variants. German total aircraft engine production across all types reached approximately 89,000 units by war's end. This included Junkers Jumo engines, BMW radials, and all Daimler-Benz variants combined. British production of the Merlin alone nearly doubled total German aircraft engine output. When American production was added, the disparity became overwhelming. Allied material advantages rendered German tactical and technical superiority increasingly irrelevant. The philosophical difference was stark. German engineers pursued perfection within each engine, accepting limited production as the cost of excellence. British engineers pursued adequacy across many engines, accepting technical limitations as the cost of quantity. German strategy assumed superior quality would overcome numerical disadvantages. British strategy assumed sufficient quality combined with numerical superiority would achieve victory. Events proved the British calculation correct. Part 3. The Cost of Truth. Werner Mulders did not survive to witness the full implications of his 1940 evaluation. On November 22, 1941, he was returning to Berlin to attend Ernst Udet's funeral. The Heinkel He 111 bomber carrying him encountered severe weather. The pilot attempted an emergency landing at Breslau. The aircraft crashed, killing Mulders and 2 others. He was 28 years old. His official tally stood at 115 victories, making him Germany's leading ace at that time. His Rechlin report on the captured Spitfire remained in Luftwaffe files. The tactical recommendations proved valuable for pilots engaging British fighters, but the deeper implications went unrecognized. Mulders had identified the Spitfire's technical weaknesses accurately. He had not grasped that those weaknesses were acceptable trade-offs within a larger industrial and strategic framework. The captured Spitfires continued serving at Rechlin and other evaluation facilities throughout the war. Later marks were examined as they fell into German hands. Each new variant showed improvements addressing earlier limitations. Constant speed propellers replaced 2-position units. Improved carburetors reduced negative G fuel starvation. 2-stage superchargers extended altitude performance. The British were systematically eliminating weaknesses Mulders had documented, but the most significant changes were invisible to tactical evaluation. Merlin production methods continuously improved. Manufacturing tolerances tightened as factories gained experience. Worker skill levels increased as training programs matured. Supply chains became more efficient as logistics organizations learned their tasks. The British were building an industrial system optimized for sustained warfare, not individual excellence. By 1943, British aircraft production exceeded German output across all categories. Fighter production particularly favored the Allies. Britain alone produced approximately 26,000 military aircraft in 1943. Germany produced approximately 25,000. When American production was added, Allied numerical advantage became crushing. United States factories produced approximately 85,000 military aircraft in 1943. Combined Allied production exceeded 100,000 aircraft annually, while Germany struggled to maintain 25,000. The engines powering these aircraft told the same story. Merlin production continued expanding. American factories added Allison, Wright, and Pratt & Whitney engines to Allied output. German production remained constrained by material shortages, labor limitations, and strategic bombing. The RAF and USAAF could replace losses within weeks. The Luftwaffe required months to rebuild depleted units. The Battle of Berlin, fought from November 1943 through March 1944, demonstrated the cumulative effect. British Bomber Command dispatched approximately 16 major raids against Berlin, totaling 9,000 sorties. German defenders inflicted serious losses, shooting down approximately 500 bombers. But British factories replaced the lost aircraft within months. Bomber Command continued operations at high intensity throughout the period. German defenders could not sustain equivalent replacement rates. The strategic bombing campaign against German industry compounded these problems. Raids targeted aircraft factories, engine plants, and ball-bearing production facilities. Messerschmitt plants at Regensburg suffered repeated attacks. Daimler-Benz facilities at Stuttgart were systematically bombed. Production declined despite desperate efforts to disperse manufacturing to underground facilities and remote locations. By late 1944, German fighter production actually increased through extraordinary efforts. Albert Speer's rationalization of production methods, dispersal of manufacturing, and ruthless prioritization of fighter aircraft achieved record output. But engines remained the limiting factor. Sophisticated power plants could not be produced as quickly as airframes. Many completed fighters sat waiting for engines that never arrived. The Americans who examined German aircraft facilities after the war documented this industrial reality. The United States Strategic Bombing Survey conducted comprehensive assessments of German production capabilities. Engineers toured Messerschmitt factories, Daimler-Benz plants, and Junkers facilities. What they found confirmed that German industry had been organized for producing hundreds of aircraft. Allied industry had been organized for producing hundreds of thousands. German factories relied on skilled labor, precision tooling, and sophisticated manufacturing methods. These approaches produced excellent aircraft and engines but could not scale to wartime requirements. Allied factories, particularly American facilities, used mass production methods, interchangeable components, and simplified assembly processes. These approaches produced adequate aircraft and engines in overwhelming quantities. The lesson was clear but required decades to fully absorb. Technical excellence in individual components matters less than systematic effectiveness across complete production systems. The best engine means nothing if you cannot produce enough of them. Superior performance means nothing if you cannot maintain it under operational stress. Engineering perfection means nothing if it prevents scaling to wartime requirements. British engineers understood this from necessity. They faced potential invasion by a superior military force. They lacked resources for extended development programs pursuing perfection. They needed adequate weapons in sufficient quantities to survive immediate threats. The Merlin embodied this philosophy completely. It was good enough to compete with German engines tactically. It was simple enough to produce in necessary quantities strategically. It was reliable enough to maintain under wartime conditions operationally. German engineers understood excellence but misunderstood sufficiency. They believed superior quality would overcome numerical disadvantages. They assumed tactical advantages from better equipment would translate to strategic victory. They designed engines for peacetime development programs where refinement and optimization were possible. They failed to recognize that wartime requirements fundamentally differ from peacetime preferences. The Spitfire examinations at Rechlin revealed German engineering bias in their conclusions. Mulders had praised German engineering sophistication while criticizing British simplicity. Doppler's team had documented Merlin construction as crude compared to Daimler-Benz precision. Both assessments were technically correct. Both missed the strategic point. British simplicity was not a failure to achieve German sophistication. It was a deliberate choice to optimize different criteria. This realization came slowly to surviving German engineers. Many spent post-war years in Allied employ, working at facilities that had defeated them. They saw American and British production methods firsthand. They understood finally that losing the war had not resulted from inferior engineering or inadequate pilots or poor tactics. It had resulted from industrial organization inadequate to sustain multi-front warfare against opponents with superior production capacity. The Merlin served beyond the war, powering transport aircraft, trainers, and specialized applications well into the 1950s. Over 168,000 engines were built. Many thousands logged tens of thousands of hours in commercial and military service. Reliability improved continuously as operators learned optimal maintenance practices. The engines proved remarkably durable despite their wartime reputation for requiring frequent overhauls. Post-war evaluations reassessed the Merlin with clearer understanding. It was not the best piston engine ever built by most technical measures. The Rolls-Royce Griffon offered superior performance. The Pratt & Whitney R2800 provided more power. The Napier Sabre showed advanced design. But the Merlin was arguably the most successful piston engine ever built, when success is measured by operational impact rather than technical specifications. It powered the fighters that won the Battle of Britain. It equipped the bombers that destroyed German industry. It enabled the escort fighters that defeated the Luftwaffe over Germany. It served in enough variants and applications to influence nearly every aspect of the air war. And it did all this while being simple enough to produce in overwhelming quantities by factories with limited precision capabilities employing semi-skilled workers. The examination Werner Mölders conducted in August 1940 revealed technical truths about the Spitfire and its Merlin engine. Those truths helped German pilots exploit weaknesses and achieve tactical victories. But the examination missed a more profound truth. Technical excellence matters less than industrial capacity in modern warfare. The side that can produce adequate weapons in overwhelming quantities will defeat the side producing superior weapons in inadequate numbers. This lesson transcended the specific comparison between Merlin and DB601 engines. It applied to tanks, artillery, small arms, and every other weapon system. German Tigers were superior tanks to American Shermans by most technical measures, but American factories produced 50,000 Shermans, while German factories produced fewer than 2,000 Tigers. Numerical superiority overwhelmed technical advantages. The British had understood this principle instinctively. Fighting for national survival with limited domestic resources, they optimized for quantity and reliability over perfection. The Merlin embodied this philosophy in every design decision. It was not the engine British engineers would have designed in peacetime with unlimited resources. It was the engine they could design, produce, and maintain while fighting a desperate defensive war. German engineers had pursued a different philosophy. They assumed German technical superiority would prevail through quality rather than quantity. They designed engines that embodied engineering excellence. They created weapons that demonstrated German industrial capability. But they failed to design for the reality of industrial warfare against opponents with vastly superior production capacity. The captured Spitfire that Mölders flew in August 1940 taught the Luftwaffe how to fight that specific aircraft more effectively. It did not teach them how to win a war of industrial attrition. That, a lesson came too late, taught by factory raids, material shortages, and the inexorable mathematics of production rates. By the time German leadership understood that quantity had become quality through sheer mass, the war was already lost. Today, aviation museums worldwide display Rolls-Royce Merlin engines alongside Daimler-Benz power plants. Technical specifications accompany each exhibit: power output, displacement, weight, RPM limits. Visitors can compare the engines directly, examining construction methods and design philosophies. Most conclude that German engines show superior engineering sophistication. That conclusion is technically correct and strategically irrelevant. The Merlin won its war not through individual superiority, but through systematic effectiveness. It achieved its objectives not through perfection, but through adequacy, combined with quantity. It secured victory not by being the best engine, but by being good enough, producible in necessary numbers, and maintainable under operational stress. Werner Mölders would have understood this eventually. He was too intelligent not to grasp the implications as the war progressed. But he died in 1941, when German victory still seemed possible, when tactical excellence still appeared sufficient, when the industrial tide had not yet turned decisively against Germany. His Rechlin evaluation remains a monument to technical assessment, conducted without strategic context, accurate in every detail, yet missing the point completely. The Rolls-Royce Merlin taught a lesson that transcended aviation. In modern industrial warfare, the side that can produce adequate weapons in overwhelming quantities defeats the side producing superior weapons in inadequate numbers. British engineers learned this lesson from necessity. German engineers learned it too late. The cost of that education was measured in destroyed cities, lost battles, and a war that technical excellence could not win. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.